let's get started. So where we left off yesterday was we learned a new way to answer our hypothesis questions. The way that we did in the previous class was we left everything in terms of the units of the problem. So in the last problem that we did, it was in terms of grams of fat for those pastry items. But then what we also did last class was we converted everything to z values. And one of the things that we kept coming up with yesterday was we said we always want to compare apples to apples. So that's why whenever we were doing the first method, we converted absolutely everything to grams of fat, including the critical values, which is where our rejection regions begin. And we also had our test statistic, which was at 7.65 grams of fat. We left all those things in terms of grams of fat. But then one of the things that we said was if we're going to compare our test statistic to our critical values, another thing that we can do is convert everything to z values, and that's what we did with method number 2. So where we're going to start off today's class is just doing another example with converting everything to grams of, not grams of fat, but just the units of the problem for question number 2, which is here just going to be dollars. And then in method number 2, we're going to convert everything again to a z or a t value. All right, so let's just go ahead and get this started off. The mayor of a large city claims that the average net worth of families in the city is at least $300,000. A random sample of 100 families selected from the city produced a mean net worth of $288,000 with a standard deviation of $80,000. Using a 5% significance level, can you conclude that the mayor's claim is false? So the first thing that we're going to do here is convert everything to the units of the problem, which, like I already said, is simply just dollars. All right, so first things first, how do we know that this is a Chapter 8 question? Awesome, so we're trying to conclude about some kind of claim, so therefore we know this is a Chapter 8 question, and whenever we're doing Chapter 8 questions, our first step is always to write down our null and our alternative hypotheses. Whenever we're writing down our null and our alternative hypotheses, we always ask ourselves 3 questions. The first question is there a statement which contains equality? Is there such a statement here?
Yes, at least.
Is at least $300,000. Awesome. So what symbol is at least $300,000? Greater than or equal to, so that becomes what? Our null hypothesis. Awesome. So greater than or equal to $300,000. And the second question that we're going to ask ourselves is there a statement which does not contain equality? Do we have such a statement here? We do not. Awesome. So if we do not have a statement for our alternative hypothesis, what does our alternative hypothesis become?
It's going to be less than 300.
Awesome. Strictly less than 300,000. And then the third question that we ask ourselves is what parameter are we interested in? Are we dealing here with the mean or with proportions? Mean. So therefore, our parameter of interest is mu. So that's our first step, writing down our null and alternative hypothesis. Are there any questions about this whatsoever? Then our second step is to draw a picture so we understand where our rejection regions are. It says that our population is normally distributed, so we know that we can deal with a bell-shaped and symmetric distribution. One of the first things that we want to figure out is how many rejection regions do we have? Just one rejection region. Why do we just have one rejection region?
Is that when it's not equal sign?
Awesome. The thing that tells us where our rejection region is our alternative hypothesis. If we look at our alternative hypothesis, we have the symbol strictly less than. We said that we can use this symbol, and if we can draw a horizontal line and turn this thing into an arrow, then that arrow is going to point to where our rejection region is. So therefore, we're going to have one rejection region, and it's on the left. The only time that we would have 2 rejection regions is if our alternative hypothesis would have the symbol not equal. We would have 2 rejection regions. All right. So here we just have one rejection region. That rejection region is on the left. So therefore, we're only going to have one critical value, which again signifies where our rejection regions begin. And since that critical value is on the left tail, we're going to use the symbol C, not C prime. All right, and then in this one rejection region, we can put all of our alpha level. And what is alpha equal to here in this problem? Alpha is equivalent, is a synonymous term for significance level. So therefore we know that alpha is equal to 5% or 0.05. Everybody good with this so far? Then the other thing that came up last class, I want to make sure that I write it down on this graph here too, is where is this distribution centered on? This distribution is centered on our hypothesized value. And what's our hypothesized value in this problem? $300,000. Awesome. Another symbol that we use for our hypothesized value is mu sub naught. All right, so that's the picture for step 2. Then step 3 is we want to ask ourselves those two questions that we always started off in chapter 7, which was, is n greater than or equal to 30? And is sigma known? So let's answer those two questions. Here, do we have a sample size that's greater than 30?
Yes.
We do? Do we know the population standard deviation sigma? No. We answered yes to one, no to the other. Are we using Z's or T's? Awesome. So now we can also signify this cutoff right here, this critical value, as a Z. And now this is really, really important because this is the first time that we're going to be doing this differently. This is now a Z sub alpha, not a Z sub alpha divided by 2. Why is it only a Z sub alpha? Awesome. We only have one rejection region. It's just on one side, so therefore we're putting all of alpha into this one rejection region, not splitting alpha up into 2 rejection regions. So therefore we only care about Z sub alpha. All right, so let's take a minute for yourselves and see if you can find the Z value that corresponds to 0.05. 1.645. Awesome. Everybody good with 1.645? Technically, just to make this picture a little bit more accurate, I'm going to write that it's negative 1.645. But you guys are right. Once we get to our formula, we're just going to plug in the positive value, which is going to get us down here to step number 4. In step number 4, what are we doing in step number 4? What's the overarching goal in step number 4? So it's not the test statistic, but we are converting stuff.
We're converting it to say $3,000.
Awesome. So what we're doing here is we're going to convert our critical value, which is the beginning portion of our rejection region. We're going to convert this critical value to the units of the problem. So here the units of the problem are in dollars. Right now we only know this critical value in terms of a Z value. So we want to convert a Z value back to an X. So we want to convert this critical value, which we currently know is negative 1.645. We want to convert that back to an X value, and we're going to use this formula for it right here. This formula right here is really just an algebraic manipulation of our Z value formula. Z is equal to X minus mu over sigma. We're just writing it a little bit differently here. All right, so let's go ahead and plug in our values. What is our hypothesized value? 300,000, so we're going to plug that in for mu. We just said that Z sub alpha was equal to 1.645. Then our sample standard deviation is equal to what? 80,000, and our sample size is 100. All right, is everybody good with this step right here? What we've done in this step.
So with problems like this, you would never use the mean until the end, basically? The 288,000?
Yes, that's right. Okay, so what's the 288,000? The 288,000 is telling us if we take a sample, where on here does that sample
That's
lie?
right, okay.
Right? So the way that I think about it is this. You can think of that 288 as like your dart, right? What we're just doing right now is we're still setting up our dartboard.
Right.
And then at the end, we're going to throw the dart at it to see where the dartboard lands.
Okay. Yeah, because I keep keep like wanting to say that's the alternative hypothesis, like at the very beginning.
Yeah, it's
But,
not. That's a very common thing to do, though.
Yeah.
So I'm glad that you're saying that. And sometimes people try to plug it in right here, but it's not. Remember that those two numbers must always be the same. These two always have to be the same. All right, if you do this arithmetic, you're going to come up with a critical value that is $286,840. $286,840. All right, what does this number mean? Try to put this into words. What does this mean?
But anything that is less than the cutoff,
That's our cutoff. That anything is less than that,
we reject.
we reject, right? So this is what's happening, right? A mayor comes to you and goes, hey, the average income of people in my city or net worth or whatever it is $300,000. And you're just like, wow, that seems like a lot, right? Like, I don't know where this person's living, but, that seems like a lot of money, right? You're like, well, let me go out and test that. So you're going to say, all right, so I'm going to go out and test it, and I want to figure out a cutoff where I'm going to call this mayor a big fat liar, right? He's saying that it's at least $300,000. So if you come back and you say, hey, it's actually $400,000, are you going to call the mayor a liar? No, because it's above you. He's saying it's at least. Same thing if it was $500,000, you wouldn't call him a liar. The only cutoff that you're establishing is a lower end cutoff. That's why we're looking at something that's less than $300,000. If you go out and you take a sample, and the sample average is less than $286,840, you're going to call the mayor a liar. All right, is everybody good with that? Does that make sense what this number represents? All right, so that's step number 4. We just converted this critical value then to $286,840. That's our cutoff, below which we're going to call the mayor a liar. So, now this is getting to like what I just said about the dartboard. Our dartboard is set. Now what we're going to do is we're actually going to go out and take that sample. So therefore in step number 5, we're looking at our sample average. And our sample average in this problem is what? $288,000. So we're going to use this number to test whether or not the mayor's hypothesis is true. Does that make sense? So therefore, what is the vocabulary word for this value? It's our test statistic. Good. So this right here is therefore our test statistic. It's a statistic because it's coming from the sample, and we're using that statistic to test a hypothesis, so therefore it's called a test statistic. All right, so you guys tell me. Are we calling the mayor a big fat liar? No, because $288,000 is greater than $286,840. So therefore, $288,000 would be like right here. 288,000. So it's just above it. So it means it's outside of our rejection region. And therefore, we're going to say that since X bar, which is equal to $288,000, is strictly greater than $286,840, which is our left-hand side critical value, we do not reject the null hypothesis that mu is greater than or equal to $300,000. Everybody good with this?
Kind of.
Kind of?
I mean, I understand it, like the whole process of it, but looking at it just like from a logical standpoint, like 288 is still less than 300,000.
Right. But it's just like this, right?
So it's not like at least.
It's not at least 300,000. You're right. So let's say this happens, right? Let's make it a little bit more ridiculous. let's say the mayor comes out and goes, hey, the average income in my city is $300,000. And you're like, all right, that sounds cool. Like, I want to move to your city, but let me test this out first. You test it out, and you get that it's $299,999. Would you call the mayor a liar? No. 299,998. Right? So what we're doing is that we're establishing this cutoff. And you're right that 286,000 is like $14,000 below it, right? And to you and me, that might be a whole lot of money, right? But if you compare that to $300,000, that's like less than 1%. It's like a half %.
Okay.
Right? Does that make sense?
Yeah.
So what we're saying is that this number right here is really like a half of a percent below it, and we're less than a half of a percent. So you're right, like the numbers are big, but in the grand scheme of things, we're just giving him a tiny little bit of wiggle room.
Okay.
Cool?
Yeah, that makes a lot more sense.
Cool. Everybody else good with this as well? All right. So this was our method number 1. This is something that we did actually 2 classes ago. Now we're going to get to method number 2. This is the thing that we looked at last class. And what I keep comparing these things to is I keep saying that, hey, we always want to compare apples to apples, right? So what we just did here is we initially looked up our critical value as a z-value because we can get this z-value based off of our alpha. We've done this like a whole bunch of times now this semester. But we don't want to compare 288,000 to a z-value of negative 1.645. That would be comparing apples to oranges. Right? So that's why we converted this critical value to a dollar amount. Now we can compare dollars to dollars and we're apples to apples. In method number 2, what are we going to do? Cool. So we're going to leave this right here as a z-value. We're not going to compare it to 288,000. Instead, what we're going to do is we're going to convert 288,000 to a z-value, right? So we're going to convert our test statistic to a z-value or a t-value, right? I keep saying z-value or a t-value, but here because we're using z-values, we know that we're going to convert this test statistic to a z-value. Yeah.
And so because the test statistic is above the cutoff, even though it's not at least 300,000, that's okay.
That's okay, right? Because all that we're going to say is, are we going to call the mayor a big fat liar, right? And what we're saying here is that, hey, we're off by a little bit. He's off by a little bit, well, at least for our sample. But that doesn't mean that we're going to call him a big fat liar. Because remember this, right? We have sampling variability. What do I mean with that is, the mayor makes this claim. We go out and we check 100 households. But what happens if like those 100 households are like in the poor section of the city, right? So then, yeah, we maybe got a low number, but that's not the mayor's fault, right? Does that make sense?
Yeah.
So even though our sample came out to be a little bit less, that doesn't mean that his hypothesis is incorrect. So if we came up with a number of $300,000, $300,001, well, now we definitely wouldn't call him a liar, right? Because here he can have as much wiggle room as he wants, but down here below we're only going to give him a little bit of wiggle room, but he still fell within that little bit of wiggle room. Yep. Great question. All right. So is everybody good then that for method number 2, we're essentially just going to convert our test statistic to a z-value. And then we're going to compare z's to z's. All right. So let's do it. We said that the only real difference then is that we're converting our test statistic to a z-value, which means that step number 1 stays the same. Step number 2 stays the same. Step number 3 stays the same. And then step number 4. What's different about step number 4? We don't need it, right? Because the whole purpose of step number 4 was to convert the z-value to dollars, but we don't want to convert the z-value to dollars. We want to leave it as a z-value, so we say that we don't need this. Step number 5. Does anything change about step number 5? formula, right? So we're saying, yep, this is like now the main thing that's going to change in the second method, and that is that we need to change this test statistic to a z-value. But if I ask you, how do you convert a test statistic to a z-value, especially if you're in the heat of the battle while you're taking the test, you might blank on it, right? It's like the fog of war for test taking. So if you're in the fog of war for test taking, you always have this crutch, and your crutch is your formula sheet. So now what we're saying here is this. We're trying to convert a test statistic to a z-value, so we know that we're going to be somewhere here in this column because this is our test statistic column. The only thing that we've really dealt with so far in these tables is just from here and above, right? Just inference about single population means and inference of a single population proportion. Those are the only ones that we've used so far. And we know that we're not dealing with proportions, so we're only dealing with means, so we're somewhere here in this category. Well, if we try to figure out where we are up here in this portion of the table, we already said that we have a sample size greater than 30, so we know that we're going to be up here. But we also said that we do not know our population standard deviation sigma, so we're going to be right here. If we follow that over to our test statistic column, this is the formula that we're going to use to convert our test statistic to a z-value. Everybody good with that? All right. So then I'm going to copy this down, and I'm going to say now that z is equal to x bar minus mu sub naught divided by s divided by the square root of n. All right. X bar we already identified in the first method, and it's also given to us in our problem. It's 288,000. What is this mu sub naught thing again? It's $300,000. It's our hypothesized mean. So that's what we're getting from our hypothesis. And then our S, you guys already told me that this is 80,000, and our sample size is 100. So we get this right here. Everybody good with plugging in the values? All right, if you do this arithmetic, you end up with negative 1.5. Simple enough. We have that our test statistic is negative 1.5. Can't quite scroll up all the way without losing this. So I'll give you guys a second to copy this down. All right, so we have that our z value is negative 1.5. And what I keep referring to this to, especially today, is I keep calling this our dart. Well, we just threw our dart, and our dart landed on negative 1.5 on our dartboard, and our dartboard is our picture that we made of step number 2. So if we land at a z value of negative 1.5, are we in our rejection region or not? Again, we're not, right? Here our rejection region begins at negative 1.645, which is why I emphasized writing that negative up here earlier. Negative 1.645. So we just found out that this is another way of saying a z value of negative 1.5. So therefore, we're not in our rejection region. So therefore, we're going to arrive at the exact same conclusion, just worded a little bit differently. And we're going to say that our test statistic, which is negative 1.5, is strictly greater than negative 1.645, which is our left-hand side critical value. Therefore, we do not reject the null hypothesis that mu is greater than or equal to 300,000 doll hairs. Yep, everybody good with this? All right. Here's one thing that I want to point out that sometimes the common final exams are really, really sloppy about. So sometimes this is also something that people have questions about whenever they're doing the homework. Because like I said in the past, your guys' homework are just past common final questions, right? And that is this. just like we did with our critical values, where we said we're going to call one of them C and the other one C prime, in math and stats in general, we're very, very specific about giving two different things a distinct name. That's why we're calling one C and the other one C prime, so we always know which one we're talking about. But what we're doing here, too, is if you think about it, right here, we're calling $288,000 our test statistic, because we're using that to test our hypothesis. But we're also calling this number down here, the negative 1.5, we're also calling this our test statistic. So one time we're calling a z-value a test statistic, the other time we're calling it something that here is in dollar a test statistic. So therefore, technically speaking, the distinction is that we're going to call something that has units, we're going to call that our test statistic. And once we convert it to a z-value, we're going to call this our standardized test statistic. So once we convert it to a z-value or to a t-value, we're saying that we're standardizing our test statistic. So this is the technically 100% correct way of calling the z-value of negative 1.5. But, like I said, the past common finals tend to be really sloppy about this. Now, how does that affect you? You're going to read a problem, and it's going to say, find the test statistic. And you're going to be like, well, I know how to do that. Like, I'm just going to look up to see what it says is the sample average in the problem. Right? Then the problem is that all the answer choices are going to be in terms of z-values. So technically speaking, it's not asking you to find the test statistic. It's asking you to find the standardized test statistic. Right? So if you see a question and it says find whatever it is, I always recommend glance at the answer choices, see what format the answer choices are in. That way you're going to know how to go about answering these types of questions.
Some of this SS stands for correlation regression.
No. So what you're asking is this down here, this SS. This SS stands for sum of squares. And again, it has a little bit to do with finding the line of best fit for a set of data. What I said last class when we briefly talked about this, I think it was before I actually started recording, the difference between one of these points and your line of best fit, that's what we're going to call our error, and that's what we're going to try to minimize whenever we're trying to find the line of best fit. We're going to say that the line of best fit has the smallest amount of error for every single point. Well, that's difference. That's what we're going to call our error, and we're going to end up squaring that difference. So that this one, if it's positive, doesn't get subtracted by this one, which could be negative. If we square them, we're getting rid of the positives and the negatives. So we're going to square them first, and then we're going to add them. So if we're squaring them first and then adding them, that's why we have sum of squares. Makes sense? But we're not going to really get into that. Definitely not today. Great question. All right, how do you guys feel about method number 1 and method number 2? Anybody want to do another example? Let's do another example. All right. PepsiCo contends that the average bottle which it produces in the Carolinas contains exactly 20 fluid ounces. A random sample of 25 bottles are selected with an average content of 19.9 fluid ounces and a standard deviation of 0.3 fluid ounces. Using a 95% confidence level, can you conclude that PepsiCo's claim is false? All right. As always, how do we know that this is a Chapter 8 question? Awesome. We're trying to test some claim. So therefore, whenever we're trying to test some claim, if we're trying to convert everything to the units of the problem, here, what are the units of the problem? Awesome. So we're going to first start off this problem by writing our null and our alternative hypothesis, and everything that we do after this, we're always going to do in terms of fluid ounces. All right. Step number 1, writing our null and alternative hypothesis. We know now that at this point, whenever we're trying to write our null or our alternative hypothesis, we always ask ourselves three questions. The first question is
there equality?
there a statement which contains equality? Do we have such a statement here? We do, and it says exactly 20 fluid ounces, so what symbol is that? And what does that become, our null or our alternative? And the second question that we ask ourselves is there a statement which does not contain equality? Do we have such a statement here?
It will just be like U is not equal to the point.
Awesome, right? Because we already used up this sentence right here for our null hypothesis. The next one after that talks about the sample. And the next one after that is just telling us what to do. So therefore, we do not have a statement which does not contain equality. So therefore, our alternative hypothesis becomes the complement or not equal to 20 fluid ounces.
I have a question.
Yes.
So is it always going to be not equal to, or could it be less than or greater than equal?
Great question. We're always going to use the complements in this scenario.
Okay.
The only time when we're, especially for this class, the only time that we're going to have an option where it can be one or the other is if we have the alternative hypothesis, but we do not have the null,
Okay.
right? Because then we can use the complement or we can use equals to,
Okay.
right? Good?
I got tripped up on that with homework.
All right. Does that make sense now, though?
Yes.
Awesome. Then the third question that we're going to ask ourselves is, what's our parameter of interest? Are we dealing with averages or proportions? Averages. All right. Second step that we're going to do is we're going to draw our picture. Here, then, we're going to have our bell-shaped symmetric distribution. How many rejection regions are we going to have? 2. Because we're always going to look at the symbol for our alternative hypothesis to determine where our rejection regions are. Here we have not equal to for our alternative hypothesis, so therefore we have 2 rejection regions. Which means that we're going to split alpha up equally into our 2 rejection regions. So how big is alpha here? 5, so therefore alpha divided by 2 is 2.5%, or 0.025. We also have 2 critical values, since we have 2 rejection regions. The left one, as always, we'll call C, and the right one we'll call C prime. And what is our distribution centered on? 20 fluid ounces, which is our hypothesized value, mu naught. Everybody good with this picture? Our third step then is to do what? Awesome. Do we have a sample size greater than 30?
No.
Do we know sigma? So therefore we use what? T-values. Hey, friend. Alright, so we use T-values. Our next step then, well, let's go back and figure out what these T-values are, because now these things are going to be T sub alpha divided by 2's. Whenever we're trying to figure out what the T-value is, we need to know 2 things. What are those 2 things that we need to know? Degrees of freedom and our alpha divided by 2, which is what we already know is 0.025. How many degrees of freedom do we have in this problem? 24. Since we have a sample size of 25, we have 24 degrees of freedom. So if we go to our T table, to the column for 0.025, and we come down here to 24 degrees of freedom, we're going to get a T value of 2.064. Everybody good with 2.064? So therefore, we know that this T value over here is going to be 2.064. This one's going to be negative 2.064. Everybody good on this so far? All right. Step number 4. What are we trying to do in step number 4? Good. We're trying to convert our critical values now from T values to fluid ounces. So we're going to try to convert both C and C prime to fluid ounces. And in order to do that, we're going to have mu minus t sub alpha divided by 2 times s divided by the square root of n, or mu sub naught plus t sub alpha divided by 2 times s divided by the square root of n. Everybody good with this so far?
Could you not do plus or minus?
You could do plus or minus now, right? Like if you wanted to somehow include both of these together and do a plus or minus, since we have two cutoffs, you could do the plus or minus thing. But you couldn't. What you couldn't write is you couldn't write this, just this portion right here, right? Because that's technically. Oh, sorry, plus or minus. Because that technically is incorrect. Because now you're saying that C is equal to both of those, which isn't quite right.
Okay.
Right? Does that make sense?
Yeah.
So if you just say something like critical values equal to, then that would be right.
Okay, that makes sense. Thank you.
Cool. Sure. Right. Then let's plug in our values. Here we said that our hypothesized value is 20 fluid ounces, our standard deviation is 0.3, and our sample size is 25. And we know that our t-value is 2.064. If we do that for both of these, we're going to end up with this. And doing the arithmetic on this, we end up with 19.88 and 20.12. Is everybody good with this? All right. Then, the next step that we're going to do is to identify our test statistic. And here, our test statistic is 19.9. Which is just our sample mean. Alright. I keep calling this test statistic like your dart. You just threw a dart at the dartboard and it landed at exactly 19.9. Did it fall inside the rejection regions or not? So here we have 19.9. Here our left-hand side critical value is 19.88, and here it's 20.12. Is 19.9 in a rejection region or not? No, it's like just outside, right? It's like just here. Like you were trying to aim for like the bullseye, and you just got like a hair outside the bullseye, so you didn't quite get it, right? So we're just outside of our rejection region. So therefore, we're going to say that since, and now this becomes important because we have to signify that we're in between the two rejection regions. We're going to say that C, which is equal to 19.88, is strictly less than 19.9, which is equal to x bar, but that is also strictly less than 20.12, which is equal to C prime. So all I'm saying here is that 19.9 is in between 19.88 and 20.12. And I'm including the symbols here that x bar is in between C and C prime. We reject the null hypothesis. Oh, we do not reject the null hypothesis. We do not reject the null hypothesis that mu is equal to 20 fluid ounces. Alright, I know some of you are sitting there thinking, hey, wait a second. This is really darn close, and had I rounded, we would have been right on the line, right? So I know you're thinking of probably two questions at this point. And the first question is probably this. If you land right on the critical value, you're still in the rejection region. Right? So if you land on the critical value, you're still in the rejection region. Even if it's, so the critical value is still part of the rejection region. Right? Is everybody good on that point? The second point is this. No, you're never going to see questions that are this close on your homework or your exams, where rounding it one way or the other is going to affect suppose you hadn't carried two decimal places, you had only carried one decimal place, you probably would have arrived at a different conclusion, and the numbers are not going to be that close on the exam or on the homework.
Can you go over again how you distinguish between whether there's one or two cutoff points?
Yes. So here, whether or not we have one or two cutoff points depends on whether or not we have one or two rejection regions. And how many rejection regions we have and where those rejection regions are only depends on our alternative hypothesis. So the only thing that we're ever going to look at is our alternative hypothesis. Now, if you remember from our discussion for our alternative hypothesis, the only symbols that we can ever have for our alternative hypothesis is strictly greater than, strictly less than, or not equal to. Those are the only three possible symbols that we can ever have. Well, the quick and easy method that I showed you guys was this. If you look at the alternative hypothesis, and you change this thing into an arrow by drawing just a horizontal line, then that arrow is going to point to where your rejection region is. So here, if we had strictly greater than, we would just have one rejection region on the right. Same thing too, if we make this into an arrow, it's pointing to the left, so therefore we're going to have one rejection region and it's going to be on the left. However, if you have the symbol not equal to, you can't just draw a horizontal line and make it into an arrow, right? Like that just wouldn't look right. So therefore, here in this case, since we don't have an arrow that's just pointing to one side, we're going to have two rejection regions on both sides. Or one rejection region on each side. Does that make sense?
Yes.
So therefore, here, once we set up our null and alternative hypothesis, we looked at our alternative hypothesis, saw that it was not equal to, we realized that we couldn't just draw a horizontal line that would point one way or the other, so therefore we had two rejection regions with two critical values. Did that answer your question? Yes. Cool. Any other questions about any of this? All right. Then what's the main difference between method number 1 and method number 2? Step number 4, right? So step number 1 through 3. So 1 through 3 is the same. Then we're going to get to step number 4. And in step number 4, the main difference is what? Good. We don't do it, right? Step number 4 we don't do. And Betsy, I think you are ready on to step number 5. What's the difference about step number 5? Cool. We're going to change this one value right here, our test statistic. We're going to change that to either a Z or a T. Which one are we going to change it to here? YT?
Because our sample size is not bigger than 30 sigma, right?
Yeah, sigma is not known. Awesome. Because here we determined that we are dealing with T's, so therefore here we're going to change this to a T as well. So now you're probably saying, well, how do I change it to a T? What's the formula for that? Awesome. Awesome. So we have this right here. And if you're wondering, where did Betsy get this from? Again, we have a sample size that's less than 30 now. We don't know sigma. We can come over here to our test statistic column. Here's the formula for our test statistic. So that's the formula that Betsy just said. So if we wanted to plug in values into this, then we still have an X bar of 19.9. Our hypothesized value is what? 20. So mu sub naught is 20. S is equal in this problem of 0.3, and our sample size is still 25. If you do this arithmetic, I'll spare you the arithmetic, it comes out to negative 1.67. So now we have a t value of negative 1.67. Now that we have a t value of negative 1.67, let me first ask you guys, what is the technically correct term for this t value? standardized test statistic. Good. So this right here is our standardized test statistic. And what are we going to compare the standardized test statistic to? Awesome. Negative 2.064 and positive 2.064. So now, obviously, negative 1.67 is between those two values. And now, what does this also allow us to see? Exactly, right? Like, up here, we said, whoa, like, had we rounded, we would have gotten this wrong, right? But now, if we round this to the next decimal place, we're at negative 1.68. We're still pretty far off from negative 2.064, right? So again, what this is going to allow us to do is not just arrive at the same conclusion as we did for method number 1, but we're going to get a little bit more of a sign of how far away we are. All right. So therefore, here, we're going to say that since C, which is equal to negative 2.064, is strictly less than T, which is equal to negative 1.67, which is strictly less than 2.064, which is equal to C prime, we do not reject the null hypothesis that mu is equal to 20 fluid ounces. Which again, all I'm saying here is that our T value is in between our two critical values. All right, how do you guys feel about this example? You guys starting to see that we're always just following the process and what the process is doing? Does the process make sense, like intuitively, what we're trying to do here too? Cool. Awesome. Great. All right. What we're going to do now is this. What we're saying here is that we're either comparing units to units, here is fluid ounces to fluid ounces, or we're comparing Z values to Z values, or in this case it's T values to T values. But one of the things that we could do too is this. And this is going now a little bit back to what we did previously. Here we had the example of, I'm going to try to draw this a little bit bigger. Here we had negative 2.064, and we had positive 2.064. And then we found out that we had some critical value, and this critical value was negative 1.67. So I'll just draw this right here. Right, this is what we had in the previous problem. Forget for a second that it was T values. Just imagine for a second that these are Z values, not T values. The reason why I want you guys to do that is I think you guys feel a little bit more comfortable with Z values because we've been using it for a little bit of a longer time. And the concept is exactly the same. One of the things that we did to identify this 2.064 was we said that from here down, right, of course. That pen's like, no, it's Friday, I'm out of here. All right. Here, from here on down, we said that here we had 2.5% of our data, and then from here up, we also had 2.5% of our data. That's how we initially got those 2.064. And then what we did was, in the previous two methods, we either compared T values to T values, or we compared fluid ounces to fluid ounces. But one of the things that we could also as equally do is we could say, hey, I know how to calculate out the percentage of this shaded area. So one of the things that I could also do is I could compare, or I could calculate out the percentage of this graph that is below my test statistic. Oh man, did 2 pence die all on one go? All right, here we go. No, this one's just being lazy. All right, we could compare the percentage of the graph that is below this point, which I just tried to shade as red, to the percentage of the graph that is below this point. Right? Does that make sense? We could compare percentages of the graph to the percentages of the graph. Well, which one is bigger here? The percentage of the red or the percentage of the black? Right? The red one is greater. Right? Is everybody good that the red one is greater? Alright, well, if the percentage of the red one is greater than the percentage of this black one, then that means then that this point has to be outside of the rejection region. Right? Does that make sense? If the red was smaller than the black, so let's say like the red was like over here, well, then that point has to be within our rejection region. So all that I'm saying here is this. We can compare fluid ounces to fluid ounces. We can compare T values to T values. Or we can compare percentages to percentages. It's just another way of doing the exact same thing. Right? Is everybody good with that? So now what we're going to do is we're simply just going to practice the percentages to percentages. And when we compare percentages to percentages, we're looking at the p-value approach. We're going to start looking at p-values. And the p-value, to be really, really specific, the p-value is going to be the percentage of the red. Right? So we're going to calculate out what the percentage of the red is. We're going to call that our p-value. And then our p-value, we're going to compare it to alpha to see which one is bigger or smaller.
So is that what we use, like, say the t-score or the v-score to figure out what's going to be the percentage?
Yes, exactly. So, like I said, forget that we're dealing with t's here for a second, right? Let's just call this thing right here as z. You just found out that your z-score was negative 1.67.
So then you go to the, okay.
You go to the table, you find that percentage,
Yeah.
and then you're going to compare that percentage to our alpha number, right? All right.
I really struggle on that part of the homework.
Okay, but good. After this discussion, I think it's going to go a lot easier.
I thought it was like some really complex things that like you need to like be taught to learn, and now I'm learning.
Nice.
I was
I'm
like,
glad.
like YouTube it in like Khan Academy.
Yeah,
Yeah.
yeah.
Then you can take it the first time.
You know, whenever you encounter anything for the first time, it's always a little bit difficult, right? But one of my favorite phrases to hear is, "Oh, that's it."
I get it.
Oh, that's it. All right, so let's take a look at this real quick. This is like the introductory type stuff for p-values, and we're now in section 8.3. If you look at section 8.3, here we have that p-value that I was just talking about, but we also give it its own name besides p-value. So what we're going to call the p-value is the observed significance. Those two things are synonymous. It's a lot easier to say p-value than observed significance, so I'm going to use the phrase p-value, but they're the same thing. All right, so technically speaking, the observed significance of a test of hypotheses is the probability on the supposition that H naught is true, or if you assume that H naught is true, of obtaining a result at least as contrary to the null hypothesis and in favor of the alternative hypothesis as a result actually observed in the sample data. Right? The red needs to be bigger than the black, y'all. You guys good? That's all that this is saying, right? Like, words are no good. Don't become an English major. Like, that word stuff is no good, right? The black needs to be bigger than, the red needs to be bigger than the black. If the red is bigger than the black, you reject. If the black is not bigger than the red, if the red is bigger than the black, you do not reject. And if the red is smaller than the black, then we're going to reject. All right. The computational definition of the observed significance of a test of hypothesis is the observed significance of a test of hypothesis is the area of the tail of the distribution cut off by the test statistic. Now that should make a little bit more sense, right? If you look at the area of the tail that was cut off by the test statistic. Where here is our test statistic? What number is that? Negative 1.67. So the area of the tail that is cut off by the test statistic, that is what? The area of the tail that is cut off by the test statistic is what? That's the red, right? The area of the tail that is cut off by our test statistic, we're looking at the red portion. That's the area of the tail, right? So here what it's saying is that the area of the tail of the distribution cut off by the test statistic, and sometimes we're going to use it as 2 times the case of a two-tailed test. Don't worry about that. We'll get that here in just a second. All right. Then here, this is the step-by-step guide that your textbook or the textbook that accompanies this class outlines for how to do the p-value approach. Like I said previously, my approach is a little bit different, so I'll be showing you guys how to do my approach instead. So let's do it. Go to the next example. So we skipped one of these examples, so we could make sure that we do this. If we have time, we'll go back to that example that we skipped, but I want to make sure that we do at least one of these right here. All right. So let's think about this here, y'all. The main difference now for this p-value is that we're trying to compare percentages to percentages. The way that we got the percentage for our test statistic, right, that negative 1.67 that I had in the previous picture, the way that we got that red portion is by taking that 1.67 and going to the table. Right? Let me not just talk words. Let me put the picture back up here. What I'm saying is this. If you wanted to figure out how big red was, what would you do? You would go to the table and you would look at what?
You look at negative 1.6 and you go over to 7 and you'd be like 0.04 something.
Awesome. So if we wanted to figure out the size of red, we would take negative 1.67 and we would go to our z-table. Right? Everybody good with that? Mm-hmm. So therefore, what we're going to end up doing is we're going to end up comparing black to red. So therefore here we want to use negative 1.67 and we want to take that to the table. Therefore, in order to do that, we need to be using z-values. Right? Does that make sense? Mm-hmm. Is there any point whatsoever then to convert this to any kind of other unit, like fluid ounces or grams of fed or anything like that? Right? So we don't want to convert things to units. We want to convert things to z-scores, right? Or t-scores, right? Does that make sense? So therefore, what method are we building? Are we building on method number 1 or method number 2?
Method number 2.
Cool. So what we're primarily going to focus on is method number 2. But then once we get to the z-value, we're not going to stop there. Okay. We're going to take it one step farther. We're going to go to the table, and then we're going to compare percentages to percentages. Does that make sense? Mm-hmm. All right. All right, so let's do it. The total score in a professional basketball game is the sum of the score of both teams. An expert commentator claims that the average total score for an NBA games is 202.5. A fan suspects that this is an overestimate and that the actual average is less than 202.5. He selects a random sample of 85 games and obtains a mean score of 199.2 with a standard deviation of 19.63. Determine at a 5% significance level whether there is sufficient evidence in the sample to reject the expert commentator's claim. All right. There's a whole lot of words here and a whole lot of stuff going on, but if we stick to the process, we should be okay. First things first, how do we know that this is a Chapter 8 question? Cool. We're looking at some kind of claim, right? And whenever we're doing a Chapter 8 question, we're going to state our null and our alternative hypotheses. Whenever we're trying to state our null and our alternative hypotheses, we ask ourselves three questions. The first question we ask ourselves is there a statement which contains equality?
Technically, that claims that the
Average total is. Good. And the average total is 202.5. What symbol is that? Equal to, so therefore it becomes our null hypothesis equals to 202.5 points.
So is this where the alternative hypothesis is going to be like less than?
Great question. So our second question is to ask, is there a statement which does not contain equality? And do we have such a statement here?
It's
Less
less than 200.
than 202.5. So therefore, what does that become?
not equal to.
That becomes less than.
Becomes less than.
So that would mean you only have one tail, or do you still have two tails?
All right, well, let me get to that in just a second. Right? So here, what we're saying is this. The expert commentator claims this, right? So we used up that sentence. A fan suspects that this is an overstatement and that the actual average is less than 202.5. So that is then the statement that does not contain equality. So therefore, the symbol that we're going to have is strictly less than. So because we have strictly less than, that becomes our alternative hypothesis of less than 202.5. And then our third question we always ask ourselves is, what's our parameter of interest? Here we're dealing with averages, not proportions. So again, we're just using mean. All right, that's step number one. Now, Betsy, your question was about step number two. And in step number two, what we're always trying to say is, hey, we're dealing with a bell-shaped symmetric distribution. And what we're trying to do in step number two is, one of the things is identify how many rejection regions we have and where those are. So answer your own question. Where is our rejection region? It's going to be on the left, right? And only on the left. And that was the answer to your question, right?
So does that, so like, it's not clicking yet, so I'm asking.
Okay.
So like, that goes for, if it's greater than for the alternative hypothesis, it's going to be just to the right?
That's correct.
Okay, so it kind of determines on how the alternative hypothesis turns out.
That's exactly right.
And the tail, we only figure out the tail from the alternative, not from the,
Not from the null. That's exactly right.
Okay, that makes sense. Thank you.
Cool.
So basically, to add on to that, if there's not an alternative hypothesis, you would have not equal to.
Exactly.
But in this case, there is, so you would have that.
That's exactly right,
Okay.
right? So let's just say that that the fan just didn't say anything, right? And that the expert commentator said, hey, it's equal to 202.5, and the fan goes, sounds like a bunch of crap. Let me go test it out, right? Now he's not making a claim other than he thinks that you're wrong, right? So here then that would just be the complement of this, so that would mean that this would be not equal to. Now, or, like you guys also said, yeah, exactly, that would then be that. If, however, he thinks that this is an understatement and that the actual average is greater than that, well, now this symbol would become greater than, and we would have one rejection region on the opposite side, right? So that's why we're always asked that question. Is there a statement which does not contain equality? And if there is one, then that becomes our alternative hypothesis. Does it make sense now?
Yeah, it does.
Cool. Awesome. So is everybody good then that we have one rejection region, that rejection region's on the left? Are we going to split up alpha? No, because we only have one rejection region, so we're going to put all of alpha in here. And how big is alpha? 0.05, because we know that alpha and the significance level are synonymous. So therefore, we only have one rejection region. What's the symbol for that rejection region? For our critical value? C. Awesome. So we have this. All right. Everybody good with this so far? All right. The only other thing that I keep drawing on this picture is the center of our distribution, which is our hypothesized value. And we said that that is equal to 202.5. All right. Step number 3 then are our two questions back from chapter 7. And that is n greater than or equal to 30 and is sigma known. How big is our sample size? 85, so this is yes. Do we know sigma? No, we only know the standard deviation from the sample, so this is no. Everybody good with these two answers? What are we going to use? Z.
So
Alright.
wouldn't the majority of the time with these problems where we work with the z-scores?
Yes. So, and here's the reason why, right? What we're going to end up doing with this stuff is we're going to take these z's and we're going to end up going to the table.
Okay.
Because in the table then, we're going to be able to use those z's and we're going to focus in on a percentage.
Alright.
And then we're going to compare the percentages to the percentages. But if you think back to the T table, we only have very, very specific percentages that we can follow up to, right? So it's just a lot easier to make questions that deal with Z since we have all sorts of possibilities for probabilities, like for those percentages. So that's why there has yet to be a common final exam question that asks you to calculate out p-values for T's because there's just so few of them.
That makes sense.
Cool. All right, so we're going to use Z's. So then we're going to try to identify right? Remember that we're in method number 2. So one of the things that we're going to try to do is we're going to try to identify this critical value in terms of a Z. No, we're not going to do that. I'm going to skip this here for a second. I'm going to skip this, and we'll see why we're going to skip this here in a second. Well, let's just talk about it now. Why do I not need to find the Z value for this critical value?
Because you already know your percentage.
Good. You already know your percentage, right? You already know that this percentage is for this critical value. If we're going to find the Z value and later on just compare stuff to this percentage anyways, why are we finding the Z value? Like, that's just an unnecessary step, right? Does that make sense? So if we're just trying to get to percentages, we already have the percentage for this critical value. And if we want to compare percentages to percentages, there's no need to get the Z value. Does that make sense? Right. So we don't need to do that. What do we do in step number 4? You convert.
The 19 points.
You would convert your rejection value to a z-score. But since we're not good scores and z-score, you would want to make it a percentage.
You're on the right track. I just think that the wrong words are coming out of your mouth.
Okay.
Step number 4 always just did what? What was the overarching objective of step number 4?
On the critical value.
Change it to the units, right? We only don't even not care about units. We also don't care about the z-score for this, right? In this step right here, what we would always do is take this z-score and we would now convert that to points. Not only are we not interested in points, we're also already not interested in the z-score right here because we're just interested in percentage. So therefore, we definitely don't need step number 4.
So we just are following the standardized test statistic.
Good, right? So in step number 5, what we always first looked at was we said that, hey, our test statistic, what's our X bar for this problem? 199.2. And we said that this was our test statistic. Well, this is in points. We don't want it in points. What we're trying to get at is a percentage. So you're exactly right. The way that we're going to get to that percentage is first convert this to our standardized test statistic, and then do what with that? Take it to the table. Good. So let's convert this to a standardized test statistic. So I'll make this little arrow for the standardized test statistic. And then the standardized test statistic. All right. What's our formula for the standardized test statistic? And what symbol am I using for the standard deviation? Good, because we don't know sigma. Everybody good with where to find this formula if you don't remember what this formula is? Yep, the column for test statistics You just follow it based off of these two questions that we already answered. All right, so let's plug stuff in here. We now have 199.2 minus 202.5 divided by S, and S is 19.63. And our sample size, we said, was 85. Everybody good with what I'm doing up here with those values? All right, if we do this arithmetic, we end up with negative 1.55. That's the z-score for our dart. That's our test statistic, right? Now, one quick word about this negative 1.55 here. I don't really remember exactly if you actually do this, how many decimal places it came out to be, but I'm assuming that it's going to come out to more than just 2 decimal places.
Yes.
What are we going to try to do with this? Take it to the table. And the table goes to how many decimal places? 2 decimal places, right? Like here we go to 1 decimal place on this column, and then on this the top row, we're going to go to the 2nd decimal place. So therefore, whatever this comes out to be, you want to round this to 2 decimal places, just like you would round any other number, right? So if you round this, then it should come out to. Is everybody good with what I mean with that? All right. We have negative 1.55. We take this to the table, and in our table, this comes out to be what percentage? 0.0606. Everybody good with getting 0.0606? All right. We're at a percentage. Now, the important thing about this is this, and this is extremely, extremely, extremely important. This does not yet have to be our p-value. We need to check to make sure this is our p-value. So a common mistake is to immediately compare this thing right here to the area in our tail, to compare that to 0.05. But we haven't yet verified that this right here is our p-value. And here's the thing for our p-value. Let's go through this. I'm going to flip over the page. I have a little bit more room. First things first. What we want to do is we always want to compare our p-value to alpha. We're always going to compare our p-value to alpha. If the p-value is greater than alpha, we do not reject the null hypothesis. If the p-value is less than or equal to alpha, we reject the null hypothesis. Give you guys a minute to copy this down. All right, everybody good with copying this down? All right. A lot of times people forget this, right? Especially if like you're in the heat of the battle. So here's another silly analogy that I've come up with that's going to hopefully help you guys remember this. If we go back to the picture that I had on the previous page, then over here, this is always going to be our alpha. And what I had here is I had something like this, and I said that from here on down, this is the red, and we kept comparing red to black, right? Does everybody remember what I'm talking about? All right, this red in here, this is what we're going to try to identify as our p-value. So, therefore, if our p-value is greater than alpha, which we have right here in this example, we're not going to reject our null hypothesis because our test statistic has to be outside of our rejection region. Does that make sense? Everybody good with that? All right. If, however, our is less than or equal to alpha, so it's either exactly equal to black or it's less than black, then we would reject our null hypothesis. Right? Does that make sense? All right. If you somehow forget this, what I always try to tell people is you want to compare your P to your alpha. And if you forget which way these symbols have to go, what I always say is remember that alpha is like a hurdle and that your P is a runner. Who's trying to jump over the hurdle? Which is your P, right? Like your P is your runner and your P is trying to jump over the hurdle. Let me ask you this. If you have a sprinter and that sprinter doesn't make it over the hurdle, that sprinter failed, right? And that's exactly the same concept here. You want your P to be over the hurdle in order for you not to reject your hypothesis. If you run into the hurdle, right, you're equal to it, you failed, right, so you reject. And if for some reason you're less than this, so somehow like you go out and you start crawling underneath the hurdle or something like that, you also failed, right? So if you can remember that your P is like your runner trying to jump over the hurdle, you need to make it over the hurdle in order to be successful. So then you wouldn't reject the hypothesis. Does that make sense? All right. That's one thing. That's just to hopefully help you remember when you reject and you don't reject. Just a silly analogy, kind of like, there's Ebola in the classroom. But here's another really important thing, and that is determining whether or not this percentage that we're looking up, whether or not that is our p-value or if that's not our p-value. And here's this. So first things first, you're going to go through a process, and that's the process is for step number 1 is going to be, I don't know why I just drew that dot. Let me draw it as a 1 instead. All right, here's step number 1 is the standardized test statistic positive? Is the standardized test statistic positive? So for the example that we're just doing right now, is that standardized test statistic positive? What's our standardized test statistic equal to?
No.
Negative 1.55. So is the standard test statistic positive?
No.
No, it's not. If you say no to this, then you don't have to do anything. However, if you answer yes to this, then the percentage that you look up in the table, you're going to subtract that from 1. So the percentage from table subtract from 1. Everybody good with this so far? So in the example that we just got done doing, do you have to subtract that percentage from 1? No. So that's step number 1. Step number 2 then is do you have 2 rejection regions? In the example that we just got done doing, do we have 2 rejection regions? No. Again, if you answer no, you don't do anything. However, if you answer yes, then here you're going to multiply percentage in step 1 by 2. So if you have 2 rejection regions, whatever percentage that we have, we would just multiply that number by 2.
And that's just what you set aside for earlier.
So here, after you do these two steps, now you're going to have, so then 3 is, then this is your p-value. This is your p-value. After you go through those two steps, then you have arrived at your p-value. The important thing about this is this. You have to do these steps in order. It's really, really, really that you do these steps in order. Why is it important that you do these steps in order? In step number 1, you're doing subtraction. In step number 2, you're doing multiplication. In mathematics, which order you do stuff in is really, really important. You can't just change up your steps for subtraction and multiplication. Otherwise, you're going to end up at different answers. So therefore, you have to do this one first, and then you do this one. If you don't do it, if you do the opposite way around, you're going to end up with the wrong answer. Everybody good with that? Yep. All right. So let me ask you guys this. Let's go through that whole scenario now one more time, even though I already asked you guys. Is our standardized test statistic positive? No. Do we have to subtract this percentage from 1?
No.
Do we have 2 rejection regions?
No.
Do we have to therefore multiply this number by 2?
No.
No. So therefore, is this our p-value?
Yes.
Yes. So this right here is our p-value. What do we compare our p-value to?
Alpha.
Alpha. Always comparing our p-value to alpha. Is our p-value greater than alpha?
Yes.
Therefore, do we reject our null hypothesis?
No.
No. Everybody good with that?
Yeah.
So here, then our conclusion, which is always our step 6, we're going to say that since alpha is equal to 0.05, which is strictly less than 0.0606, which is equal to our p-value, we do not reject the null hypothesis that mu is equal to 202.5. How do you guys feel about this? You guys see that really the main difference that we're doing here is that we're doing method number 1 up until this point. Right? We're just converting everything to a z or to a t-value. The only additional thing that we're doing is we're taking that to our table. And after which we've done probably about 500 times this semester, taking z-values to our table. After we look up the percentage in our table, we're asking ourselves those 2 questions that I had on the back side of the sheet to run through to make sure that that percentage is our p-value. And then we're just comparing that p-value to our alpha. Right? Is everybody good with that? So the only main difference then, I'll call this our third method, is just this portion right here. And then what I have also on the back page. That's the only difference between method number 1 and method number 3. Everybody good with that? All right. So then, we've covered those 3 methods. Those 3 methods are on your homework, and they'll be on your exam. The only thing that we didn't cover from chapter 8 then is proportions, right? If you look at all of our hypotheses, they've always been just mu. They've never been p-values. Or p's, I shouldn't call them p-values now, right? Because now we know p-values are something different. So what I'm going to do is I'm going to remove the questions from your homework that deals with proportions, and proportions also will be on your guys' exam, right? But these 3 methods will be on your homework and on your exam. Is that fair?
Did you say proportions?
And not for the final either.
Proportions will not be on the test?
Proportions for hypothesis testing will not be on the test.
Okay.
Cool.